plug in, and we will get started. There we go. Bing. Okay. This is the lesson on Hamilton paths and circuits for my discrete math class. Let's see where we're going to start. First of all, today is the 9th, and we will call this Hamilton paths / circuits. There we go. Okay. First, the difference between Hamilton and Euler. For Euler paths and circuits, you had to hit every single edge exactly once. For an Euler path, you did not have to start and stop in the same location, but you could have. And for an Euler circuit, you had to start and stop in the same location, but you had to hit every single path exactly once. So for a Hamilton path, by definition, you have to visit every, if I can spell the word vertex exactly once. In order for it to be a Hamilton path, you have to visit every single vertex exactly once. For it to be a Hamilton circuit, and this is what we're going to mainly be focusing on today, you visit every vertex exactly once, except you finish where you started. So that would be the only exception. You would actually technically hit that vertex twice, the one that you started and stopped at. But you have to visit every vertex exactly once, except you finish where you started. These types of problems that you're going to be faced with that are referred to as Hamilton path and circuit problems, they are also known as traveling salesman problems, or TSP. You may see that through various problems that we may end up doing online. They may refer to them as traveling salesman problems. The general idea is that you have to visit a certain number of, well, not a certain number, you have to hit all of these different locations, but you have to do it in the optimal way possible, whether it be by spending the least amount of money, or traveling the least amount of miles, or taking the least amount of time in order to get from point A to point B to point C to point D, or whatever. To start at one location, to hit all of your destinations, and then to end up back where you started. That is the general idea behind Hamilton paths and circuits. As a side note, and this will come into play a little bit later. I'm going to put a little side note tag here. Side note. There is this concept known as complete graphs. There's this concept known as complete graphs, where every pair of distinct vertices is joined by an edge. And I will show you an example of that in a moment. Now, this concept of complete graphs is completely wrapped up in the main topic of the day, which is Hamilton paths and circuits. For example, that's terrible. This is a K sub 3 complete graph. This is a K sub 4 complete graph. The general idea behind complete graphs is that every distinct pair of vertices is joined by an edge. So in the K3 graph, it was fairly simple to see. But in the K4, let's just say A has to have a connection for B, C, and D. B has to have a connection for C, D, and A. C has to have a connection for D, A, and B. This is just the general idea behind complete graphs. You could even do, and this is probably the one that a lot of people are familiar with drawing. Make sure I just put these vertices in the correct location. This is a K sub 5 complete graph where you could have A, B, C, D, and E. That's a K sub 5 complete graph. Now, in general, just for these complete graphs, K sub n has n parentheses n minus 1 divided by 2 edges. This is going to be important later on, how many edges that you actually have to make connections for. So for example, if you were a K sub 3 graph right here, 3 times 2 is 6 divided by 2 is 3, so there's 3 edges that connect this whole thing. Or for K sub 5, it'd be 5 times 4, which is 20, divided by 2, which is 10. There are 10 connections within that graph. Basically, for these graphs, for K sub n, K sub n has a complete set of Hamilton sequences. Or, I'm sorry, circuits. What am I saying sequences for? There we go. K sub n has a complete set of Hamilton circuits, meaning you can start wherever you want, and you could, there's always a way to knock out that set of, okay, I'm going to go from A, and I got to hit all of these. I can go A, B, C, D, E, A, good. Or I can go A, C, D, B, E, A, good. Every single possible configuration, well, that's probably where the word sequence came from. Every single possible sequence you can travel, and you can complete a Hamilton circuit just by starting at any letter and finishing at the same letter. Now I'm going to back up a little bit. I'm going to talk a little bit more about this K sub 4 graph and go into a little bit more detail. There we go. So let's talk a little bit more about this K sub 4 complete graph. I'm going to draw it a little bit larger so you can see exactly what I'm referring to. There we go. Now that point in the middle where the two lines cross each other, that's not a vertex for this particular problem. It's just that there was, there were other ways we could have drawn that, but that's probably the simplest way we could have drawn that. Now, how many different possible sequences can you have? Well, it depends on where you start. If I started with A, and I wanted to traverse every single vertex, and then end up exactly where I started, which is A, I can go A, B, C, D, A. And I'm actually going to write all these out. There's not that many for this particular example if I just limit myself to starting with A. I could also go A, B, D, C, A. And because of the complete graph that's there, A, B, D, C, A. Again, with Hamilton circuits, you have to visit every vertex exactly once. Edges doesn't really matter in this case, but it's visiting every vertex exactly once. You kind of see how those connections are made. I could go A, C, B, D, A, or A, C, D, B, A, D, B, C, A, D, C, B, A. That exhausts all of the possible sequences that you could have if you just limit yourself to starting with A. Now, obviously, you could write a complete set of sequences if you started with B, or started with C, or started with D. In fact, just for the sake of argument, there are n minus 1 factorial distinct Hamilton circuits in case of n. In this case of 4 would reveal 4 minus 1 factorial is really 3 factorial, 3 times 2 times 1, which is 6. And I listed out all 6. Now, I could list them all out starting with a different letter, but the keyword is distinct. If I were to start, let's just say, with B, example, and this is important for later on. If I start with B, I could go A, D, C, B, and I had to back where I started. But here's the thing. This sequence is the same as, now watch what I do here. If I started with A, I could go D, C, B. It wraps around back to A. This sequence is exactly the same as this sequence. If I go B, actually, I'll write it in red so you can see a little bit better in the example. If I go B, A, D, C, B, it is the exact same sequence as if I did A, D, C, B, A. It's the exact same thing. That's why this definition fits. There are n minus 1 factorial distinct Hamilton circuits. Since these are the same, they are not distinct from each other. That, again, will come into play a little bit later. Now, here is the main purpose of studying the traveling salesman problem, the Hamilton circuit problem. This is kind of like an intro, kind of like, okay, I want you guys thinking about directions and sequences and what letters can actually traverse each of the vertices and things of that nature. Mirror paper. What comes into play now is the following, and I would like, if you had this copied on a separate piece of paper, that would absolutely be fantastic. I'm going to draw this a little bit larger than I did before because I'm going to have 5 vertices in this particular problem. 5 vertices. So this is like the case of 5 situation. And I'm going to make all of these connections. In total, there are 10 connections. I'm going to set this up, but now here's what's going to happen. There's a traveling salesman. Here's the scenario. A traveling salesman has customers in 5 cities. Okay? Now, he needs to schedule a trip starting in A, which is where he lives, visiting each city, and ending back in A. He needs to make a Hamilton circuit of this graph. Oh, I forgot a connection. There we go. He needs to make a Hamilton circuit. Now, obviously, we just made a whole bunch of Hamilton circuits before with case of 4. This is case of 5. But here is the problem. In order to travel from each city to the next, it's going to cost money. Now, you can consider this plane ticket cost or just road cost or something like that. But there are certain costs between each city. There is a cost in dollars. Now, obviously, some of them are a little bit harder to see than others with these connections. E to C, I'm drawing like that. I'm going to try and be very careful with how I write these numbers, so it's fairly obvious what connection they are all making. 1, 2, yeah, I think I got them all. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There are 10 connections. As we figured out in that previous formula, the n times n minus 1 divided by 2. There are 10 connections. There are 10 different prices between each city. He's got to start in A. He's got to go through every single city exactly once and end up back in A. So the problem is, what path to follow in order to spend the least amount of money. Now, we just made before 6 connections for K sub 4. Let me go back to this page real quick. These are the number of distinct connections that you could have for K sub 4. This is K sub 5. You would have to write out 5 minus 1 factorial connections. You would have to write down 24 different connections in order to exhaust this particular problem. You would write out all 24. You would have to total up, okay, what are the costs? And then figure out which one's the cheapest. Another similar issue you might be faced with, well, what if it wasn't 5 vertices? What if it was 6 vertices? If it was 6 vertices, you would have to write out 120 different sequences. I don't want to do that at all. I don't want to do that. So, we need a different method. We need something, a strategy that's going to help us figure out, okay, how can we figure out a possible optimal path? Maybe not the optimal path, but within reason, how can we determine an optimal path of this particular problem? Now, again, brute force, you could conceivably write out all 24. Good for you. But what if it was more? What if it was more? Because in reality, it's going to be more than 5 cities if you're going to be traveling around the country trying to hit all of these different locations. So, as a side note, and again, this is just another little side note from later, we could conceivably put all of this information into a table. And I'm going to do that now just so you can visibly see what's going on here. Can I fit this in? Yeah, I'll fit this in. Now, it's important that you are familiar with the table that I am about to draw, simply because it will come into play at a future date. Extend this a little bit farther. Now, again, this comes into play for Hamilton circuits. It's supposed to be an A. I had an A the first time. There we go. Now, the reason why A to B, $185. This is just an organizational table. A to C is $119. A to D is $152. And A to E is $133. Again, this will come into play. A to A, there is nothing between A and A. I'm just going to put a little dot there, or a dash, or a slash, or whatever. You want to put an X there, then by all means, you can put whatever you want, a star. Down the diagonal of this table, obviously that happens. But then you can continue. Well, okay. B to C is 121. B to D is 150. It doesn't take that long to put this table together. B to E is 200. But again, in the future, this will come into play, and this will help us with future problems. I'm just kind of showing you as a side note for the future. In fact, side note for later. This is a good organizational tool. D to C is 174. What did I do? C to E. C to E is 120. And then D to E is 199. Just that from any particular... Oh, Kyle's here. Hey, Kyle. From any one particular location, you can figure out, okay, I want to go from A to D, it's $152. I want to go from D to E, it's $199. You can use this table as an organizational tool for figuring that out. That's typically done in most of these situations. In fact, at some point you may be faced with the situation where you're just given this table and you would have to figure out most of these problems. You wouldn't even be given the visual graph, because to draw the visual graph would be next to impossible, especially if there were like 10 cities. I don't want to have to draw a graph with 10 cities. I'd rather have the table. But again, this is for future use. So the question becomes, what path do we follow in order to spend the least amount of money? We need to optimize. This traveling salesman is not going to just spend whatever dollar amount you put in front of him. He needs to figure out what would be the cheapest. There are 4 strategies that I have outlined based on the information that I have. I've kind of simplified them. But there are 4 distinct strategies that you could potentially follow to get this done. And we are going to do 3 of them. I'm not going to do all 4. You'll see why in a moment. So, and I'll bring that page back just so we can see that. Strategy 1. Strategy number 1 is known as brute force. It's also known as the... what did I write it as? Oh, exhaustive search. Couldn't read the word that I crossed out. It's also known as the exhaustive search. Brute force is literally what it sounds like. You would list out all possible Hamilton circuits, figure out cost of each, pick cheapest one. There's a lot of pros and cons to this, but I'll just keep it very simple for you. Pro. You get the optimal solution. Con. Might take forever. Now, with the brute force strategy, we could possibly use it on this example. There are 24 possible circuits that we could write out with this problem. 24 possible circuits. Again, if I were to go back here, there are n-1 factorial distinct Hamilton circuits. Well, we have 5 cities. 5 minus 1 is 4. 4 factorial is 24. There are 24 possible circuits that we could do here. You could list them all out. Good for you. I don't feel like doing that. I mean, you can, and it would work. But what if you had 6 cities? What if you had 10 cities? Let me just figure that out real quick. If you had 10 cities, that's 362,888. I'm sorry, 880 distinct circuits that you would have to list out. Why would anyone bother doing that? I don't want to. Nobody would. It's almost like I'm setting you up for a project later on. But again, we'll come back to that. Don't want to do it. So this strategy, typically use only if low number of vertices. Use only if low number of vertices. Meaning like you had a 3 or 4 or something like that. Especially me. Math is hard and less math is good. Okay, Kyle. Now let's talk about a strategy that we're actually going to use. Strat number 2. This strat is called nearest neighbor. And I'm actually going to walk you through this using our little map from earlier. So you start at home vertex. So for example, the traveling salesman had to start at A, that's where he lived. You go through cheapest edge. And I'll show you what that looks like in a moment. But basically, you go through the cheapest edge to next vertex. You continue going through cheapest edge until no new vertices, then go home. Then you just go home. Now I'll do a little pro and con, and then I'm going to show you what nearest neighbor looks like. Pro. It's simple to use. A lot less work than strat number 1. A lot less work than strat 1. You watch this in VR? That's just weird. I don't want to think about that. Con. Clearly isn't optimal. It gives you a solution, but it randomly you might accidentally be faced with, hey, I got an optimal solution. Yay, good for me. But it may or may not work. So let's actually walk through this, and I'll write the answers on a separate sheet of paper in a moment, and then I'll show you what that piece of paper looks like. So, just moving some stuff around. You have to start at A. And I'll total this all up in a minute. So, I'm writing on a separate piece of paper, nearest neighbor. And I'll show you what that looks like in a moment. Kyle says, yeah, it's like a movie theater, but I can play YouTube videos. Whatever. Anyway, so you have to start at A. If you're looking at A has 4 connections. To E, to B, to C, to D. What is the cheapest route? Well, again, you could see this a lot easier in a table down here, but the cheapest connection to A is clearly to C. And again, I'll show you what that looks like on my little side note in a moment. So now I'm at C. Now I can't go back to A. I have to go to a new city. So what, again, is the cheapest connection? I can go to B, I can go to E, I can go to D. E is clearly the cheapest one. I can't go back to A. I've already used A. So, well, I have to end up at A, yes, but I can't go back right now. I have to hit every single vertex in order to complete the Hamilton circuit. So I have to go to E next. I have to go to E next. And again, you can see that right here. C, you've already done A. E is clearly the cheapest. So now I'm at E. I can't go A, I can't go C. I have to go B or D. B or D, it's got to be D. I'm writing that down. Now from D, I don't have a choice. I can't go anywhere else except B. But now from B, I have to make the trip back to A. Here's what that would look like. For nearest neighbor, I had to go AC for the cheapest connection. I can't go backwards. I have to go to E, I have to go to D, I have to go to B, and then I have to end up at A. Altogether, that would cost me that would cost me $773. That would cost me $773. Now, is that the optimal route? I don't know. It could be. There's a chance it could be, but most likely not. So, I don't know. Just see what happens. Now I'm going to come back to this page in a moment. That's Strat 2. That is nearest neighbor. Let's talk Strat 3. Strat 3 is known as repetitive nearest neighbor. Strat number 3, repetitive nearest neighbor. Repetitive nearest neighbor. Now, it pretty much is kind of self-explanatory, except I just want to write it out. Basically, you do nearest neighbor, which is Strat 2, but use each vertex as a starting point. List each sequence with different starting point. Pick cheapest one. And again, I'll show you what that looks like in a moment. Pros and cons. Pro. It slightly improves Strat number 2. Slightly improves it. Con, takes more time to do. Definitely improves it, but it takes more time to do. So basically, I can do repetitive neighbor starting with A. I can do repetitive neighbor starting, or repetitive neighbor, nearest neighbor. I can do nearest neighbor starting with A. I can do nearest neighbor starting with B, starting with C, starting with D, starting with E. And I'm going to show you what that looks like. So, come here, you. Let's see here. This is repetitive nearest neighbor. Repetitive nearest neighbor. I already have A. So I don't have to do A again. But I mean, if you were just doing repetitive nearest neighbor from the beginning, you would definitely have to show what A looked like. So I'm going to do repetitive nearest neighbor starting with B. So let's see. If I start with B, over here, out of the way, mouse. If I start with B, the cheapest connection to B is to D, which is 100 and... No, that's not it. No, to C. What am I talking about? To C, it's 121. Let me go to this little chart here. This little chart will make me a lot happier to do with. If I'm going to start with, B, 121. It's a lot easier to see it in the chart. 121. So I'll probably do the chart next. From C, I'll move the chart down here a little bit. There we go. From C, I can't go back to B, but the cheapest connection would be A. Now, again, I'm doing nearest neighbor with a different starting location. I know the traveling salesman lives in A. We could always restructure what it looks like later. We'll deal with that. But let's just see what these connections make. C to A would be 119. From A, I can't do B and C. It's got to be E at 133. From E, the only possible connection I can make is to D, which is 199. And then I have to go back to B, back where I started, which is 150. Let's just see what that adds up to. This adds, I hear my son knocking at the door. This adds up to 722, which is clearly a lot cheaper than the first one. Okay, wow. Yeah, my son's knocking at the door. I'm going to ignore him for as long as I can because he just wants to get a stuffed animal. But already this is cheaper than nearest neighbor starting at A. I can always restructure. Okay, I'm going to have to get the door. Excuse me. James, you're being incredibly rude right now, bud. I will get him. Please step out. Come here, James. Oh, goodness gracious. Okay, and I'm finally back. Timestamps, blah, blah, blah. Okay. Repetitive nearest neighbor. I got to check it from each different starting point because you never know which one's going to be better. So I'm going to start from C. If I start from C, the closest, or not the closest, but the cheapest connection would be to A, which is 119. Then from A, the next cheapest connection would be to E, which would be 133. The next cheapest connection, which I can't do C or A, the next cheapest connection would be D, which is 199. Hopefully you see some similarities between them because sometimes that does happen. Will I have enough room? Oh, I ran out of room. Whatever, don't care. From D, I'd have to go to B. D to B would be 150. And then from B, what was that? That was a book. Anyway, from B, I'd have to go to C, which would be 121. Is this exactly the same? Yeah, I think that is exactly the same. C, A, E, D, B, C. Yeah, so that would be $722. These two are exactly the same path. Sometimes that randomly happens, but you won't know until you actually do it. Maybe I can fit in D and hopefully fit in E as well. I'm going to try and sneak them in the bottom of this page. I did not leave myself enough room. But let's just go through repetitive nearest neighbor. Again, pros and cons. Pro, it improves nearest neighbor. Con, it takes more time. It just happens. So from D, my cheapest connection is to B, yep, which is 150. Then from B, my cheapest connection would be C, which is 121. From C, my cheapest connection would be A, which is 119. From A, I have to go to E. Don't have a choice there, which is 133. And then from E, I'd be back to D. Just so happens, this again is exactly $722. You never know. You always have to double check. Let's start from E. My cheapest connection to E. This one's going to be different. C. At $120. This one's definitely going to be different. From C, I have to go to A, which is 119. From A, I can't go back to C. I can't go to E. I have to go to D. I have to go to D, which is 152. From D, I have to go to B, which is 150. And from B, I have to go back to E to end up right back where I started, which is 200. Let's see what this adds up to, because this is going to be different. Boom. $741. So, if I did repetitive nearest neighbor, I would have to do the nearest neighbor method, starting with A, starting with B, starting with C, starting with D, and starting with E, and get all of those prices. Now, it just so happened that 3 of them ended up with the same price. Doesn't always happen. But then, I am going to have to, and I may have to alter my notes just a tiny bit. Yeah, I'm going to have to alter my notes just a tiny bit in a moment. But then, I would have to change the sequence so that I was starting with A. The winning sequence for Strat 3, the winning sequence for Strat 3, I can pick any of A, to E, to D, to B, to C, which would cost me $722. Nearest neighbor by itself got me $773. Repetitive nearest neighbor got me $722. Saved himself, what, $51. That's not the last strategy I'm going to do. But let me go back to my notes just a little bit. Kyle, it can be too much math. It can be. But that's why we have computer programs to kind of figure this out when there's like 50 cities. If you had 50 cities, there's no conceivable way that I would have a human being do any of that. But if I'm giving an assessment, I can see it doing with 5 cities. Just as a little side note, a little star right here. This is important. You may have to restructure sequence with correct starting vertex. With repetitive nearest neighbor, you may have to restructure the whole thing with the proper starting vertex. Again, for example, this is what we did with nearest neighbor. Nearest neighbor, you had to start with A, you didn't have a choice. But with repetitive nearest neighbor, you can start with whichever vertex you want, and ultimately, we had a winner at $722, so we had to restructure it, starting with A, and then we would just go A, E, D, B, C, A, and that's how we got the winner for Strat 3. If we knew what all 24 sequences were, which I do not feel like listing out, Strat 1, brute force, would work every single time. But I don't feel like doing that. So instead, we're going to go to Strat 4. Strat 4. Strat 4 is kind of nice. It depends on your point of view. But it's called cheapest link. Cheapest link. Basically, mark the cheapest edge. Mark the cheapest edge. And I'm going to show you on a separate piece of paper how to do that. You're going to mark the cheapest edge. Where is my window? There you are. Cool. Then mark the next cheapest edge. Seems pretty straightforward. You would continue marking as long as you don't close the circuit too soon. You would continue marking as long as you don't close the circuit too soon. And I'm going to show you again what that looks like. And as long as a vertex doesn't have 3 edges. Ultimately, every vertex is only going to have 3 edges marked. I should put that, 3 edges marked. And then again, put a little star down here. You may have to restructure the sequence with the correct starting vertex. Let's see what this would do. Now, I'm going to bring up my map before, and I'm going to walk you through cheapest link. Walk you through exactly what cheapest link is supposed to look like. I need a fresh piece of paper. And you could do this using the map. You could do this using the chart. It doesn't really matter which one you do, just as long as it's correct. Well, let's just see. First, we start by marking the cheapest link. The cheapest link on this entire map is 119. So I have to make that connection. So I'm going to move this up. Here we go. Perfect. It's 119. And it's between A to C. A to C had 119. Cool. Now, if you're using the table, you can only use half the table, but we'll deal with that later. The next cheapest connection that I have is 120. And it's from C to E. I'm just marking the cheapest possible ones. The next cheapest one looks like 121. Right here. However, or right here. However, I can't do that one. I cannot do that because that would give me 3 edges connecting to C. And I can't do that. That would really mess up my circuit. C is already done. I cannot do C anymore. So I got to go ahead with the next cheapest link. I can't do 121. So I got to do 133, A to E. But I can't do that one either because that would end my circuit too soon. You cannot end the circuit too soon. You cannot have 3 edges coming out of the same vertices, so I can't do 133. In fact, you know what? Let me mark these off on my table just to kind of show you a strategy that you could do for this. So you already did 119, that's gone. You already did 120, that's gone. You were not allowed to do 121. You were not allowed to do 133. The next cheapest one is 150. B to D. Now, B to D is not in this yet. Let's put it down here. There's 150. And I just used that one. What's the next cheapest one? 152. A to D. Now, this looks a little weird. But I could do that. Temporarily, I'm going to have to restructure this afterwards. But A to D is 152. That marks off that. Now, if you notice, I have all 5 vertices up there. I have to make this connection next. I have to make the B to E connection, which unfortunately is 200. So let's see what this totals up to first. This totals up to 119 plus 120 plus 200 plus 150 plus 152. We got $741. And it doesn't matter what direction you go, AC or AD, but this is A, C, E, B, D, A. Cool. This is cheapest link. Now again, pro and con to this situation. Did I do a pro and con? No, I never wrote a pro and con. Pro and con to cheapest link. It's really not that hard. It's really not that long. Con, it's not optimal. It's definitely not optimal. Let me recap exactly what the heck just happened with this example with the traveling salesman before we do an example, a different type of example together. So, Strat 1 Takes too long. Skip. Strat number 2, which was nearest neighbor. Nearest neighbor got us a sequence of $773. It was short, but not optimal. We did strat number 3, which was repetitive nearest neighbor, where we listed out all 5 of them. And Kyle, this was the one that you were talking about. This took a lot of math. Yeah, it did. But it got us a path of $722. It was longer, but well, it was just longer. Longer but cheaper. There we go. That's probably what I want to say. Pro and con to the situation. That was repetitive nearest neighbor. Then we did strat 4, which was cheapest link. Cheapest link got us $741 path. It was easier and slightly better than strat 2. If I could spell strat 2. But not optimal. There's pros and cons to this whole thing. Now, I only did a sequence with 5 vertices. Clearly, we could do more. 6, 7, 8, 9, 10, a billion, doesn't matter. I'm going to show you an example in a moment. But you can see how these come into play. Strat 1, brute force. Only use it if you have a low number of vertices. Takes too long for this example, so we skipped it. Strat 2, nearest neighbor. You start at your home location, and you basically pick the connection that is the cheapest, and then keep going until you end up where you started, and you hit every vertice. It's short, but it's definitely not optimal. Strat 3, repetitive nearest neighbor. Got us a $722 one, where we had to list out all 5 nearest neighbors with a different starting point. It's longer, but it's definitely cheaper. Strat 4, cheapest link. Cheapest link, you just keep picking the cheapest number and keep going until, as long as you don't close the loop too early or the circuit too early and you don't have 3 edges coming out of the same vertex. It's easier. It's better than strat 2, but it's clearly not optimal. Strat 3 could be more optimal. It depends. Are you looking to spend less money? Are you looking to spend less time finding a way to spend less money? It's like if, for example, you needed to find plane tickets to go from, somewhere in New Jersey down to Florida. You wanted to spend a vacation in Orlando. Doesn't matter. You could fly out of Atlantic City. You could fly out of Trenton. You could fly out of Newark. You could fly out of Philadelphia. Which airline? What time of day do you go? You would have to find maybe not necessarily the cheapest, but the one that works best for you. How long are you willing to spend to find the cheapest flight? Are you willing to leave at 2 in the morning? It all depends on the person. These are different strategies that you could potentially do. Now, in the description to this video, is a link. If you click that link, it will take you to a PDF that has the example that I would like to do next. Now, I've already printed out a copy. I've already printed out a copy of this PDF. I just have to find it now. There you are. Here it is. Now, this is clearly a 6 vertice problem. This is a 6 vertice problem. How many edges are there? There are 15 edges connecting all these vertices. Again, the calculation there would be n times n minus 1 divided by 2. If you were to find the different number of sequences here, there would be 120 distinct sequences. I am not listing those out. I refuse. Instead, I'm going to walk through the 3 strategies that we can do. We're not going to do Strat 1 here. Strat 1 would take way too long. I'm going to do Strat 2. I'm going to do Strat 3. And Strat 4, I should say. So let's see what happens. Now, I could make a table out of all these. I don't feel like doing that right now, so let's just start with Strat 2. Nearest neighbor. For the sake of argument, let's just say we have to start at A. Let's just say we have to start at A. So let me get another piece of paper here. Just kind of walk you through this a little bit. Boom. So let's say for nearest neighbor, this is Strat 2. I have to start at A. For A, I can go 14, 7, 12, 5, and 9. I'm going to take the 5 route to go to C. From C, I can't go backwards. 13, 2, 6, and 3. I got to go the 2 route. I'm going to go the 2 route to E. From E, I can't go back to A. I can't go back to C. 4, 8. I can't do those, or 10. 4. 4 is the connection. From F, I can't go back to A or E. I can't go back to C. I either got to go D or B. D is 11. B is 1. Nice. I like short things like that. From B, I have to go to D. I don't have a choice, which is 15. And then from D, I'm going to go back to A, which is 12. What do those add up to? 5, 2, 4, 1, 15, and 12 add up to 39. Now, this could be dollars, this could be miles, this could be anything, really. But this is equaling 39. This is the nearest neighbor path. That's Strat 2. All right. Let's try Strat 3, repetitive nearest neighbor. Repetitive nearest neighbor. I'm going to kind of walk you through like this. I'm going to do a little side note. Again, if you want to see this image, there is a link in the description where you can go directly to this particular image that I'm working with. I am doing repetitive nearest neighbor. Now, this may take a little bit of time, but I just want to show you how quick it can potentially go. So again, if you have that link up on the side, if you kind of click that, it should bring that up. You can see exactly the hexagonal shape that I'm looking at. So from B, I'm doing nearest neighbor. I got to go F, which is 1. From F, I can go 11, 6, 4, 14. I got to go to E, which is 4. From E, I could go 8, 2. I could go 2. Yeah, let's go 2. We'll go 2 to C. There we go. From C, I can go 13. I can't go back to F. I can't go back to B. I can go to A, which is worth 5. And then from A, I don't have a choice. I have to go D. To go D, which is 12. And then I have to go back to B, which is 15. That's terrible. Let's just see if that was cheaper. And again, sometimes you may end up getting the same sequence that you had before. This one clearly was not. It's not the exact same sequence, is it? Oh my gosh, it was. Not because of the 39. Not because of the 39. It was the same sequence because look at this. B, F, E, C, A, D, B. It was the same one. Sometimes that happens. Let's try C. From C, where am I going to go first? I'm going to go 2 route to E. This could potentially be the same sequence. Let's just see what happens. From E, 10, 8, 4, 7 to... I got to go 4 to F. Sometimes you can preemptively see. Okay, this looks C, E, F. This could be the same one. Yep, I'm going to go to B, which is 1. From B, I can't go C, I can't go F. I'm going to have to go... Oh, this is interesting. I went to B, but from B, I may be able to jump directly to A. I can't go D, which is 15. Yeah, this one's going to be different. Let's go to A, which is 9. All right. From A, I can go... I can't go E, I can't go C. Oh, I don't have a choice. A, B, C, D. I have to go to D, which is 12. And then I have to go to C. DC, which is 13. Yeah, this one's going to be much different. 2, 4, 1, 9, 12, 13. And it's a 41. Again, this is repetitive nearest neighbor. It takes longer, but it is more optimal. Just see what happens. From D, I'm going to start by going... Oh, crap, that one stinks. I have to go E, which is 8. That's terrible. I got 11, 12, 15, 13. Yeah. And then from E, I'm going to go the 2 route to C. From C, I'm going to go the 3 route to B. From B, I'm going to go the 1 route to F. This one looks good. From F, I have no choice. I have to go to A. A to F is 14. And then from A, I don't have a choice. I have to go to D, which is 12. Let's see what this one gets me. 8, 2, 3, 1, 14, and 12. I got a 40. All right. Start at E. Almost there. Got a 2 route, which is to C. From C, I got a 3 route to B. From B, I got a 1 route to F. Is this going to be the same? E, C, B, F. Looks like it. From F, I have to go to A or... Oh, it's going to be different. Got to go to D, which is 11. From D, I have to go to A, which is 12. And from A, I have to go to E, which is 7. This one looks promising. 2, 3, 1, 11, 12, and 7. Yep, I got a 36. You never know. Let's start with F. F, I got to go 1 to B. From there, I got to take the 3 route to C. I got to take the 2 route to E. From E, I got to take the... No, I can't go back to F. What choices do I have? A or D? A or D? A is 7. To D is 12. And then to go back to F is 11. Let's see what that gets us. 36. Are these the same routes? Let's see. A, D, F, E. F, B, C, E. Yeah, they're the same routes. So, we found that optimal route. Now we have to reroute it. We have to reroute it in order to get back to A first. So this would be A, D, F, B, C, E, A. That would be an optimal route at 36. We'd have to reroute it. Again, I just go A, D, F, B, C, E, A. Interesting. Let's go cheapest link. Again, I wanted to walk through all 3. Repetitive nearest neighbor does take a bit of time. That's okay. Now we're going to do cheapest link. Cheapest link I am going to mark on my page, simply because it's just the easiest thing for me. Cheapest link. Cheapest link, right off the bat, I got a 1 here. Next cheapest link, I know there's a 2 in there. Next cheapest link, I know there's a 3 in there. I cannot do the 4. If I were to do the 4, I would close off my circuit. Can I do the 5? I cannot do the 5. It would cause 3 edges to come out of the C. Can I do the 6? Nope. Can I do the 7? Yes, I can. Cool. I can't do the 8. Well, hold on. 1, 2, 3, 4, 5. Yeah, the only one I haven't got is D. So I got to connect it to D somehow, but I have to connect it either from F or A. 11, 12. I have to go 11. Yeah. I have no choice. There's cheapest link. What did it get me? Well, if I went, let's just write it up here. A to E to C to B to F to D to A. That would be 7, 2, 3, 1, 11, and 12. Which, just double checking. Yep, adds up to 36. We got the exact same result as repetitive nearest neighbor, but it took us a lot less time. These are the 3 strategies that you're going to employ in this chapter, and the 3 strategies that you will eventually use on a project. I will be assigning something on this soon, and we'll see how it goes. If you have any questions, make sure you message me, but you will be getting something to practice on this very soon. We'll see you later.